Imagine standing in front of a mirror, tracing the contours of your face with your fingertips, the shape of your eyes, the color of your skin, the texture of your hair. These features that make you uniquely you were sculpted by forces stretching back millennia. Picture this: two identical twins separated at birth, raised on opposite sides of the planet. One beneath the blistering sun of the equator, the other in the frigid shadows of northern lands. Within just a few thousand years, their descendants would look entirely different. How is this possible? The question haunts the halls of anthropology. How did humans, all descended from the same African ancestors, diverge so dramatically in appearance across continents? The timescale seems impossibly short for such profound transformations. You've likely heard the standard explanation: humans adapted to their environments. Dark skin protected against intense ultraviolet radiation near the equator. Lighter skin allowed for vitamin D synthesis in sun-starved northern latitudes. But this explanation, while partially true, conceals more than it reveals. The pace and patterns of human adaptation follow mysterious trajectories that simple environmental determinism cannot fully explain. The truth is far more complex and far more fascinating. Consider the facts. Europeans and Asians diverged from a common ancestor merely 40,000 years ago. Yet they developed strikingly different adaptations despite facing similar climatic challenges. This apparent contradiction has puzzled scientists for generations. What invisible forces shaped our ancestors? What subtle environmental pressures molded the human form differently across Eurasia? And why do these differences persist even in our globalized world where geography no longer constrains human movement? Tonight, we venture into the borderlands between established science and emerging discoveries. We'll examine how UV radiation, dietary shifts, sexual selection, and genetic drift combined in unexpected ways to create the mosaic of humanity we see today. The stakes of this investigation extend beyond mere academic curiosity. Understanding the true drivers of human biological diversity illuminates our past and informs our future. It challenges simplistic narratives about race and reveals the remarkable adaptability of our species. Tonight, we will explore what conventional textbooks gloss over: the real reasons Europeans and Asians evolved so differently. The answer lies at the intersection of climate, culture, chance, and choices made by countless generations of our ancestors. Chapter 2: The Legacy Written in Our Genes. Why does this matter? Because written in our genes is a record of human ingenuity and resilience, a testament to our species' remarkable ability to thrive in environments for which we were never originally adapted. From the scorching deserts of the Sahara to the frozen expanses of Siberia, humans have survived and flourished where our closest primate relatives never could. This extraordinary adaptability is our defining characteristic as a species. Yet the patterns of these adaptations remain partially obscured, clouded by oversimplified explanations and, at times, by ideologically motivated interpretations of human variation. The real story is nuanced, complex, and far more interesting than most people realize. If we truly understand why Europeans and Asians evolved different physical traits, we gain insight into one of evolution's most fascinating experiments. We see natural selection operating not in geological time, but within the brief span of human history. The stakes of this investigation touch on fundamental questions of human identity. For centuries, physical differences between populations have been misused to construct hierarchies, justify oppression, and divide humanity into artificial categories. By illuminating the true mechanisms behind human variation, we dismantle these harmful myths. We replace them with a scientifically accurate understanding that recognizes our common origin while celebrating the diverse adaptations that enabled our global spread. Consider what would change if the common narrative about human adaptation were proven incomplete. Our understanding of medicine would transform, as we recognized how different populations might respond differently to treatments based on their evolutionary history. Our approach to public health would evolve, accounting for the varied nutritional needs and disease susceptibilities that emerged from distinct adaptive pathways. The personalized medicine revolution depends on accurately tracing these divergent evolutionary trajectories. Beyond medicine, a deeper understanding of human adaptation challenges our very concept of race. The visible differences between populations represent only a tiny fraction of our genetic variation, superficial adaptations to specific environmental pressures. These adaptations occurred through multiple, independent mechanisms rather than through a simple, linear progression. Europeans didn't become more evolved than Africans. They simply adapted differently to different environments. Similarly, the distinctive features of East Asians didn't develop because they were somehow separate from other populations. Rather, they emerged through a complex interplay of selection pressures and random genetic drift, operating on a shared human genome. What's truly remarkable is the speed of these adaptations. The most recent common ancestors of Europeans and East Asians lived just 40,000 years ago, a mere blink in evolutionary time. Yet in that brief span, dramatic differences emerged. How did this happen? The conventional explanation, that light skin evolved in northern latitudes to maximize vitamin D production, is correct but incomplete. It fails to explain the different paths taken by Europeans and East Asians to solve the same problem. Both populations developed lighter skin, but through different genetic mutations. Both adapted to cold climates, but with distinct adaptations. Both faced similar dietary challenges, yet responded with different digestive adaptations. These parallel but distinct evolutionary paths reveal that human adaptation is not a simple, deterministic process. It's a complex dance of necessity and chance, of environmental pressure and cultural innovation, of natural selection and sexual preference. Understanding this complexity matters because it undermines any attempt to rank human populations or suggest that some are more advanced than others. Each population faced unique challenges and developed unique solutions. The stakes extend to our collective future as well. As climate change reshapes our planet, understanding how humans adapted to environmental shifts in the past may provide crucial insights for navigating the challenges ahead. If we recognize that our ancestors survived dramatic climate transitions through behavioral flexibility and cultural innovation rather than just genetic adaptation, we might find hope and guidance for our current environmental predicament. Moreover, in an era of emerging genetic technologies, understanding our evolutionary history becomes increasingly important. As we gain the ability to manipulate our own genome, we must proceed with a clear understanding of how natural selection has shaped us thus far. The story of human adaptation is ultimately a story of diversity as strength. Our species didn't survive by evolving a single, optimal form. We survived by developing a remarkable range of adaptations suited to different environments. This diversity of adaptations, manifested in our physical appearances, metabolic capacities, immune responses, and countless other traits, represents humanity's greatest evolutionary achievement. It's our collective insurance policy against an uncertain future. Tonight, we will unravel this story, examining the true forces that drove Europeans and Asians to evolve differently despite their recent common ancestry. The answer will challenge conventional wisdom and reveal a more nuanced picture of human evolution. And in understanding our past more clearly, we may just find the wisdom to navigate our shared future with greater compassion and insight. For in the end, the story of human diversity is also the story of our fundamental unity. Chapter 3. Out of Africa, the journey begins. To understand why Europeans and Asians evolved different traits, we must first return to where our story began: Africa, the cradle of humanity. Approximately 300,000 years ago, the first anatomically modern humans emerged on the African continent. These early Homo sapiens were already remarkably adaptable, capable of surviving in environments ranging from lush forests to arid savannas. Their dark skin, dense with melanin, protected them from the intense equatorial sun, preventing DNA damage while maintaining proper folate levels. Their bodies were adapted for heat dissipation rather than heat conservation, with proportionally longer limbs and more efficient sweating mechanisms. These adaptations served them well in the tropical and subtropical environments of Africa. For nearly 200,000 years, humanity remained primarily an African species. Small bands of hunter-gatherers spread across the continent, developing distinct cultural traditions but maintaining relatively similar physical characteristics adapted to equatorial conditions. Then, around 70,000 to 50,000 years ago, something remarkable happened. A small group of these African humans crossed the narrow strait at the southern end of the Red Sea and began humanity's great diaspora across the globe. The timing was fortuitous. Earth was in the grip of the last ice age, with sea levels significantly lower than today. This created land bridges in some regions and shortened water crossings in others, facilitating human migration across previously impassable barriers. These pioneering humans carried with them the genetic legacy of Africa, but faced entirely new environmental challenges as they pushed into the Eurasian landmass. The selection pressures that had shaped their ancestors for hundreds of millennia suddenly changed. The consequences were dramatic. As humans moved north, they encountered less intense sunlight, particularly less ultraviolet B radiation, the wavelength that both damages DNA and enables vitamin D synthesis in the skin. This created an evolutionary dilemma. The dark skin that had protected their ancestors from DNA damage and folate degradation now prevented them from producing sufficient vitamin D, crucial for calcium absorption and immune function. Vitamin D deficiency has severe consequences: rickets in children, osteomalacia in adults, compromised immune systems, and reduced fertility. In the new northern environments, natural selection would strongly favor genetic variations that allowed for adequate vitamin D production. But this was just one of many new challenges. As humans pushed northward, they encountered progressively colder climates that their heat-adapted African bodies were ill-equipped to handle. Cold stress can be just as lethal as heat stress. The cold, dry air of northern winters created selection pressure for changes in body shape and proportions. Shorter limbs conserve heat by reducing surface area. Narrower nasal passages warm and humidify cold air before it reaches the lungs. Simultaneously, these migrating humans faced new dietary challenges. Moving away from year-round plant abundance meant greater reliance on animal proteins and fats, requiring digestive adaptations. Seasonal food scarcity created pressure for efficient energy storage. Around 45,000 years ago, these migrating humans reached a crucial geographic bifurcation in their journey. Some groups continued northwest into what would become Europe, while others moved northeast into the steppes of Central Asia. This divergence marked the beginning of separate evolutionary paths. Though both groups faced cold climates and reduced UVB exposure, subtle differences in their environments would ultimately lead to distinctly different adaptations. The European environment featured cloudy, humid conditions with dense forests. The Asian interior, particularly the steppe regions, experienced extreme continental climate patterns: intensely cold, dry winters, and hot summers with clearer skies. These environmental differences created distinct selection pressures. But equally important were the different cultural adaptations each group developed. Culture, often overlooked in discussions of physical evolution, played a crucial role in human adaptation. Consider clothing. Both European and Asian populations needed protection from cold, but the specific designs, materials, and coverage of their garments differed based on available resources and cultural preferences, altering their exposure to sunlight. Similarly, dietary customs evolved differently. European populations incorporated dairy farming, creating selection pressure for lactase persistence, the ability to digest milk into adulthood. East Asian populations developed different culinary traditions. Shelter construction, fire management, hunting techniques, and social structures all developed along different trajectories, creating distinct cultural niches. These cultural differences imposed different selection pressures on the genes of each population. This interaction between genes and culture, what scientists call gene-culture coevolution, accelerated human adaptation beyond what genetic changes alone could achieve. It helps explain the remarkable speed of human evolutionary divergence. By 30,000 years ago, distinct populations had established themselves across Eurasia, each beginning to develop unique adaptations to their local environments. The stage was set for the dramatic divergence in physical characteristics we see today. Yet another factor would soon amplify these differences: the last glacial maximum around 20,000 years ago. As massive ice sheets expanded across northern latitudes, human populations retreated to separate refugia, isolated areas where survival remained possible. This period of geographic isolation, lasting several thousand years, allowed genetic differences between populations to accumulate. When the ice retreated and populations expanded again, they carried with them the distinct genetic signatures of their refugia. What emerges from this complex history is not a simple, linear story of adaptation, but a rich tapestry of parallel evolution, cultural innovation, genetic drift, and occasional interbreeding between diverging populations. The traditional narrative of human races evolving as separate lineages is fundamentally incorrect. Instead, we see a complex network of populations exchanging genes while adapting to local conditions through both biological and cultural means. This understanding transforms how we view human diversity. The physical differences between populations represent not separate evolutionary paths, but creative solutions to similar challenges, achieved through different combinations of the same genetic toolkit. Chapter 4. The UV Paradox. The first major clue to understanding why Europeans and East Asians evolved differently lies in their relationship with sunlight, specifically ultraviolet radiation. Both populations moved to regions with significantly less UV exposure than their African homeland. Yet despite facing this similar challenge, they developed distinct genetic solutions. This UV paradox represents one of the most fascinating examples of convergent evolution in human history, different populations arriving at similar adaptations through different genetic pathways. Let's examine what happened. As humans moved north, the reduced UV exposure created strong selection pressure for lighter skin to maximize vitamin D production. Without sufficient vitamin D, children developed rickets, adults suffered bone diseases, and fertility declined. In Europeans, several genes underwent mutations that reduced melanin production. The most significant changes occurred in a gene called SLC24A5, which accounts for 25 to 40% of the skin color difference between Europeans and Africans. East Asians also evolved lighter skin, but through different genetic pathways. They carry distinct mutations affecting genes like OCA2 and MC1R. These mutations reduce melanin production, but in ways biochemically different from the European adaptations. This represents a classic case of convergent evolution, different populations independently evolving similar traits to solve the same environmental challenge. But why different genetic solutions? The answer likely involves both chance and subtle environmental differences. When a population encounters a new selection pressure, natural selection works with whatever genetic variation happens to be present. Random mutations that occurred in the European population differed from those in Asian populations. Additionally, the specific UV environments differed. Europe has a maritime climate with frequent cloud cover, while much of East Asia experiences clearer skies, but more extreme seasonal variations in temperature and UV exposure. These subtle differences may have favored slightly different adaptations. Europeans evolved exceptionally light skin to maximize vitamin D production during brief summer exposures, while East Asians balanced UV protection with vitamin D synthesis differently. But the UV paradox extends beyond skin color. Europeans and East Asians also evolved distinctly different eye shapes, nose structures, and hair textures, all potentially influenced by their relationship with ultraviolet radiation and climate adaptation. The epicanthic fold, the skin fold of the upper eyelid that covers the inner corner of the eye, is common in East Asian populations but rare in Europeans. Why did this feature evolve in one population but not the other? One hypothesis suggests the epicanthic fold provided protection against extreme cold and glare from snow in the Central Asian steppes. The fold reduces the exposed eye surface, protecting against freezing winds and intense reflected sunlight. European populations, living in more forested environments with less extreme wind conditions, may not have experienced the same selection pressure. Different environments selected for different eye adaptations even at similar latitudes. Nasal structure provides another example of divergent adaptation. Europeans typically developed narrower, more protruding noses, while East Asians evolved wider, flatter nasal structures. Both represent adaptations to cold air, but through different morphological solutions. The narrow European nose creates a longer air passage, warming cold air more efficiently before it reaches the lungs. The wider East Asian nose may reflect adaptation to extreme continental dry cold, where humidifying inhaled air becomes equally important. Hair texture also diverged significantly. Europeans typically have wavy or curly hair with round cross-sections. East Asians developed straight, thick hair with circular cross-sections. These differences may reflect adaptations to humidity and temperature regulation. The straight, Thick hair common in East Asia provides better insulation against cold while allowing efficient heat dissipation in summer. The more variable hair textures in Europe may reflect adaptation to the more consistently humid conditions of the region. These physical differences emerged rapidly in evolutionary terms, developing over just 30,000 years or approximately 1,000 generations. This pace of change suggests extremely strong selection pressures were at work. But here's where the story takes an unexpected turn. Genetic studies reveal that these visible differences represent a tiny fraction of our total genetic variation. Humans are remarkably similar genetically, more similar than many other mammalian species. This creates a paradox of its own. How could such dramatic physical differences emerge from such genetic similarity? The answer lies in the nature of the genes that control our physical appearance. Many of our physical characteristics are controlled by a small number of regulatory genes that have outsized effects on development. Small mutations in these genes can produce dramatic changes in physical appearance without affecting most of our genome. These regulatory genes often control the timing and duration of developmental processes rather than coding for specific proteins. They act as switches and dimmers that alter how other genes express themselves during growth. When natural selection acts on these regulatory genes, it can produce rapid, visible change while leaving most of the genome untouched. This explains how Europeans and East Asians could develop such distinct appearances while remaining genetically similar. But this is only part of the story. Recent genetic evidence has uncovered something even more surprising. Some of the most important adaptive mutations in both Europeans and East Asians didn't arise through standard natural selection at all. Instead, they came from interbreeding with archaic human species. Europeans received adaptive genes from Neanderthals, while East Asians inherited beneficial variants from both Neanderthals and another archaic group, the Denisovans. This genetic inheritance from ancient cousins accelerated adaptation to new environments. Neanderthals and Denisovans had lived in Eurasia for hundreds of thousands of years, evolving adaptations to local conditions that modern humans could acquire through interbreeding. The story grows even more complex when we consider sexual selection, mate choice based on physical appearance. Different beauty standards and mate preferences in separated populations likely amplified the physical differences that initially emerged through natural selection. As certain traits became more common in a population due to natural selection, they may have become preferred in mates, creating a feedback loop that accelerated divergence between populations even after the original environmental pressures diminished. All these factors, different UV environments, distinct regulatory gene mutations, archaic human interbreeding, and divergent sexual selection, combined to create the distinct appearance of Europeans and East Asians despite their recent common ancestry. But the most startling discovery has emerged only in the last decade, challenging everything we thought we knew about human adaptation. Evidence now suggests that the traditional explanation for skin color variation, the vitamin D hypothesis, is incomplete. New research indicates that protection against folate degradation by UV radiation may have been equally important in driving skin color evolution. Folate is essential for DNA synthesis and repair, especially during pregnancy and fetal development. This discovery forces us to reconsider the simplistic latitude-based explanation for human skin color. If both vitamin D synthesis and folate protection shaped skin evolution, then the adaptations we see must reflect a complex balance between competing needs. And that's where we encounter the most perplexing question of all. If Europeans and East Asians faced similar challenges in balancing vitamin D synthesis and folate protection, why did they evolve such different physical characteristics beyond just skin color? The answer appears to lie in a complex interaction of factors we're only beginning to understand. Factors involving migration patterns, population bottlenecks, dietary shifts, and cultural practices that created subtly different selection pressures across Eurasia. But to fully grasp this mystery, we must explore evidence that has been largely overlooked in traditional accounts of human evolution, evidence that points to forces beyond simple environmental adaptation shaping the diversity of human appearance. In the next part of our exploration, we'll examine how dietary revolutions, social structures, and even parasitic diseases may have played crucial roles in driving Europeans and East Asians along different evolutionary paths despite their shared genetic heritage. The evidence suggests a far more complex and fascinating story than we've been told. A story where chance events, cultural choices, and subtle environmental differences combine to create the remarkable diversity of human appearance we see today. Chapter 5. Beyond the Surface. The standard narrative of human adaptation to different environments explains much about our evolutionary divergence, but it leaves crucial anomalies unexplained. These contradictions reveal deeper forces at work, forces that challenge our understanding of why Europeans and Asians evolved such different traits. Consider this peculiar fact. Europeans and East Asians both evolved light skin, but Europeans generally have lighter eyes and hair color, while East Asians retain dark eyes and hair. If reduced melanin production were purely for vitamin D synthesis, why this partial divergence? The traditional explanation suggests that light eyes and hair in Europeans were simply byproducts of selection for light skin. But this fails to explain why East Asians, who faced similar vitamin D pressures, didn't develop the same traits. Recent research points to sexual selection as a key factor. Once light eyes and hair appeared in European populations through random mutation, they may have been preferred as attractive and distinctive, creating a feedback loop that amplified these traits through mate choice. But this raises another question. Why didn't similar sexual selection operate in East Asian populations? The answer may involve different cultural beauty standards and mate selection criteria that emerged in isolated populations, amplifying initially minor physical differences. Another anomaly concerns cold adaptation. Both Europeans and East Asians faced frigid Ice Age conditions, yet developed different physical adaptations to cold. East Asians typically have more subcutaneous fat, shorter limbs, and other features specialized for extreme cold. Europeans, despite facing similar temperature ranges, evolved different cold adaptations. This suggests that the specific type of cold, dry continental versus humid maritime, may have created distinct selection pressures despite similar temperature readings on a thermometer. Perhaps the most perplexing contradiction involves noses. European populations typically evolved narrow, protruding noses, while East Asians developed flatter, wider nasal structures. Both represent adaptations to cold air, but through completely different morphological pathways. The narrow European nose creates a longer pathway to warm cold air before it reaches the lungs. The wider East Asian nose may better humidify extremely dry continental air. Subtle environmental differences selected for different solutions to similar problems. These contradictions become even more intriguing when we examine tooth morphology. East Asians commonly display shovel-shaped incisors, front teeth with raised edges forming a shovel-like shape. This trait is rare in Europeans despite its potential functional advantages. Recent genetic analysis revealed something remarkable. The gene for shovel-shaped incisors was inherited from Denisovans, an archaic human species that interbred with the ancestors of East Asians, but had minimal genetic contribution to European populations. This suggests that chance historical encounters between populations, who happened to meet and interbreed with which archaic humans, played a crucial role in determining which adaptive traits spread in different regions. The anomalies continue when we examine earwax. Yes, earwax. East Asians predominantly have dry earwax, while Europeans have wet, sticky earwax. This seemingly trivial difference results from a single genetic mutation with surprising implications. The same gene that produces dry earwax also reduces underarm odor by affecting apocrine sweat glands. Research suggests this mutation spread rapidly through East Asian populations about 15,000 years ago, indicating strong positive selection. But why would reduced body odor be so strongly selected in East Asian populations, but not in Europeans? Some anthropologists propose it relates to different population densities or cultural practices regarding personal space and hygiene that emerged during the last glacial maximum. Another puzzling contradiction involves alcohol metabolism. Many East Asians carry mutations in alcohol dehydrogenase genes that cause the Asian flush reaction, facial reddening, and discomfort after alcohol consumption. This trait is much rarer in Europeans. These alcohol-related mutations spread through East Asian populations starting around 10,000 years ago, coinciding with the development of rice agriculture and rice wine production. Europeans, despite developing their own alcohol traditions, didn't experience the same selection pressure. This suggests that different agricultural practices and dietary innovations created divergent selection pressures even when both populations had access to similar resources. Cultural choices shaped biological evolution in unexpected ways. Lactase persistence presents another fascinating anomaly. Many Europeans evolved the ability to digest milk into adulthood, while this trait remains relatively rare in East Asian populations. Both groups domesticated animals, so why the difference? The answer likely involves different cultural practices regarding dairy consumption. European pastoralists relied heavily on milk as a food source, creating strong selection pressure for lactase persistence. East Asian cultures typically processed milk into low-lactose products like yogurt. These contradictions reveal a crucial insight. Human evolution wasn't driven solely by environment or genes, but by the complex interaction between biology, culture, chance historical encounters, and the particular innovations each population developed. Consider the consequences of the invention of cooking. All human populations cook food, but different culinary traditions expose people to different compounds, temperatures, and food processing methods, potentially creating distinct selection pressures on digestive enzymes. Archaeological evidence shows that European and East Asian populations developed different cooking technologies and food preparation methods. These cultural differences may have created subtle selection pressures on genes related to taste, digestion, and metabolism. The anomalies extend to disease resistance as well. Europeans and East Asians evolved different immune adaptations in response to local pathogens. The Black Death that devastated Europe selected for resistance genes that didn't spread in East Asian populations. Similarly, different parasitic diseases in East Asia created selection pressures absent in Europe. These distinct disease environments likely contributed to subtle differences in immune function that persist today and affect how different populations respond to modern diseases. Perhaps the most perplexing contradiction involves brain evolution. All human populations have essentially identical brain sizes and capabilities, yet certain genes related to brain development show evidence of recent positive selection that differs between Europeans and East Asians. These brain-related genetic differences don't affect intelligence. All human populations have the same cognitive potential. Instead, they may involve subtle differences in neural architecture, neurotransmitter levels, or other aspects of brain function shaped by distinct cultural environments. For example, some research suggests differences in the prevalence of certain dopamine receptor variants between populations, potentially influencing average temperament and behavior in ways that might have been advantageous in different social structures or subsistence patterns. These contradictions and anomalies force us to abandon simplistic explanations for human diversity. The differences between Europeans and East Asians weren't solely determined by latitude, UV levels, or temperature, but by a complex web of factors. Historical contingency played a crucial role. Which mutations randomly occurred in which populations, which archaic humans they encountered, which cultural innovations they developed. All these chance events shaped the trajectory of human evolution. The implications are profound. Human biological diversity represents not a ladder or a tree, but a network, a complex pattern of adaptations reflecting our remarkable ability to thrive in diverse environments through both biological and cultural means. As we'll see in the next section, these scientific insights align with certain traditional myths and legends that may contain kernels of truth about our ancient past, stories that hint at the real reasons Europeans and East Asians evolved such different physical characteristics. Chapter 6. Echoes from the Ancient World. Throughout human history, myths and legends have attempted to explain the diversity of human appearance. While many of these stories reflect cultural biases rather than biological realities, some contain surprising kernels of truth that align with modern scientific discoveries. Ancient Chinese texts describe the Western barbarians as having deep-set eyes, high-bridged noses, and hairy bodies, traits attributed to their exposure to harsh winds and rugged terrain. These observations reflect genuine physical differences that emerged through adaptation. Similarly, European accounts of East Asian peoples often noted their distinctive eyes, describing them as adaptations to steppes and deserts. These pre-scientific attempts to explain human variations sometimes intuited connections between environment and physical traits that modern research confirms. But these ancient accounts also contain something more intriguing: hints of lost migrations, forgotten contacts between distant peoples, and ancient knowledge about human origins that went unrecorded in conventional histories. Consider the enigmatic Darim Basin mummies discovered in western China. Dating back 4,000 years, these perfectly preserved bodies display distinctly European features: long noses, red and blonde hair, tall stature, yet they were buried in the heart of Asia. Their presence suggests population movements more complex than our standard historical narratives acknowledge. These were not isolated travelers, but established communities with their own distinctive cultural traditions, living thousands of miles from their genetic relatives. DNA analysis confirms these mummies were indeed genetically European, specifically showing affinities with ancient steppe populations. Their existence points to extensive early contact between European and Asian populations that likely influenced the gene pools of both regions. Chinese historical records mention these white-skinned, green-eyed people living in western regions. They were known as the Yuezhi and Wusun, described as distinct from both Chinese and Mongolic peoples. These accounts preserve memories of complex population dynamics. What's particularly intriguing is that some Darim Basin mummies show signs of both European and Asian characteristics, suggesting admixture was occurring. These ancient hybrid populations may have contributed unique adaptive traits to both European and East Asian gene pools. Similar evidence comes from the opposite end of Eurasia. Ancient DNA from early European farmers shows genetic contributions from Middle Eastern populations that brought agriculture northward, introducing new adaptive traits to European populations. These population movements weren't simple, unidirectional migrations, but complex back-and-forth exchanges that created a genetic tapestry far more intricate than the simplified out-of-Africa narrative suggests. Genes and adaptations flowed in multiple directions. Ancient myths sometimes preserve memories of these migrations. Norse legends speak of the Aesir gods coming from Asia, potentially reflecting actual population movements. Similarly, Chinese legends of Western kingdoms may contain kernels of historical truth about ancient contacts. Even more intriguing are myths about human origins. Many cultures preserved stories of ancient environmental catastrophes that forced human adaptation and migration. These narratives, once dismissed as mere fantasy, align with paleoclimatic evidence of rapid climate shifts. The biblical flood story, echoed in numerous cultures worldwide, may reflect memories of rapidly rising sea levels at the end of the last ice age. These flooding events would have forced coastal populations to migrate inland, mixing with established groups and stimulating new adaptations. Chinese myths speak of great floods during the time of Emperor Yu, while numerous indigenous traditions describe environmental changes forcing ancestral migrations. These stories, transmitted across countless generations, may preserve memories of real events that shaped human evolution. But perhaps the most provocative out-of-place evidence comes from genetic studies of isolated populations that don't fit neatly into our standard narratives of human migration and adaptation. The Ainu people of northern Japan exhibit physical characteristics unlike their East Asian neighbors: wavy hair, light skin, heavier facial hair. Genetic studies suggest they represent an ancient lineage that diverged early in the peopling of East Asia. Their distinctive traits may preserve adaptations from an earlier wave of migration that was largely replaced by later populations with different adaptive traits. The Ainu represent living evidence of alternative adaptive pathways that were possible in East Asian environments. Similarly, certain isolated Siberian populations show unusual combinations of European and East Asian traits that don't match our expectations. These populations may preserve evidence of ancient hybrid zones where different adaptive strategies converged. The Tibetans present another fascinating case. Their high-altitude adaptations, increased oxygen efficiency at elevation, came from genes inherited from Denisovans. Without this archaic human DNA, Tibetans might never have adapted successfully to their mountain environment. This Denisovan contribution to Tibetan adaptation reminds us how contingent human evolution can be. Had Tibetan ancestors not encountered and interbred with Denisovans, the entire trajectory of Asian population history might have unfolded differently. Perhaps the most provocative out-of-place evidence involves the EDAR gene, which affects hair thickness, tooth shape, and sweat gland development. A specific variant of this gene is nearly universal in East Asians, but rare elsewhere. Genetic dating indicates this EDR variant rose to high frequency in East Asian populations about 35,000 years ago, long before the last glacial maximum. Its rapid spread suggests it provided some significant adaptive advantage, but its function remains partially mysterious. Recent research suggests the EDR variant may have been selected for its effects on mammary gland branching, potentially enhancing nutrient delivery during breastfeeding in vitamin D-poor environments. This connection between seemingly unrelated traits reveals the complex nature of adaptation. But the EDR story gets stranger. The same variant appears at high frequency in Native American populations, but is nearly absent in Europeans, despite all three groups facing similar northern climates. This pattern defies simple environmental determinism. The distribution of this gene creates a paradox. If it was so beneficial for cold adaptation, why didn't it spread in European populations? The answer may involve the timing of migrations, founder effects, and the distinct cultural adaptations each population developed. Ancient DNA provides additional out-of-place evidence. Analysis of a 24,000-year-old Siberian boy revealed a genetic profile showing both European and Native American affinities but little connection to modern East Asians, despite being found in Asia. This suggests that population movements and replacements in Northern Asia were far more complex than previously thought. The genetic landscape of ancient Eurasia was a dynamic mosaic, with populations carrying different adaptations expanding, contracting, and mixing over time. Even more recently, archaeological discoveries in southern China revealed human remains dating to about 14,000 years ago, with an unexpected mixture of archaic and modern features. These findings suggest that human evolution in East Asia followed unique pathways. The remains, found in Malyadong, Red Deer Cave, show a combination of traits not seen in other populations: broad cranial features alongside more modern dental characteristics. They may represent yet another branch of humanity that contributed to the modern East Asian gene pool. What emerges from these myths, legends, and out-of-place evidence is a picture far more complex than our standard narratives acknowledge. A history of human adaptation shaped by cultural choices, chance encounters, and forgotten migrations. The real reason Europeans and East Asians evolved different physical characteristics isn't simply about latitude or climate, but about the unique historical trajectories each population followed. Trajectories influenced by who they met, what they ate, how they lived, and who they chose as mates. Chapter 7. What hangs in the balance? As we piece together the complex puzzle of human adaptation, the stakes of our investigation grow increasingly apparent. This isn't merely an academic question about our past. It has profound implications for our present and future. The way we understand human diversity shapes how we approach medicine, how we view social differences, and even how we might adapt to future environmental challenges. Getting this story right matters for reasons that extend far beyond scientific curiosity. Consider the medical implications. When we recognize that Europeans and East Asians adapted to similar environments through different genetic pathways, we gain crucial insights into why different populations respond differently to certain medications and treatments. The field of pharmacogenomics, studying how genetic variation affects drug response, reveals that medications for heart disease, psychiatric conditions, and cancer often work differently in different populations due to distinct evolutionary histories. Beta blockers, commonly prescribed for hypertension, show varying effectiveness across populations. The same is true for certain antidepressants, antipsychotics, and blood thinners. These differences reflect distinct evolutionary pathways that shaped each population's biology. For example, some East Asian populations metabolize alcohol differently due to variants in alcohol dehydrogenase genes that spread during their unique agricultural history. This affects not only alcohol tolerance, but also how certain medications are processed. Similarly, lactase persistence in Europeans influences gut microbiome composition, potentially affecting how oral medications are absorbed. These population differences emerge through the distinct adaptive paths we've been exploring. Understanding these divergent evolutionary trajectories allows for more personalized medicine. Rather than assuming a one-size-fits-all approach, doctors can consider a patient's evolutionary background when determining optimal treatments and dosages. But the implications extend beyond medicine to our understanding of human psychology and behavior. If physical traits evolve differently in response to similar environments, might the same be true for certain aspects of psychology? Research suggests subtle population differences in the frequency of genes affecting neurotransmitter systems, potentially influencing average temperament, stress response, and social behavior. These differences reflect adaptations to distinct cultural and environmental contexts. To be absolutely clear, these differences don't imply superiority or inferiority, nor do they override individual variation or cultural influences. They simply reflect different adaptive strategies that worked in different historical contexts. Consider the implications for understanding cultural differences. If European and East Asian populations adapted to similar challenges through different biological pathways, they likely also developed different cultural solutions to these same challenges. Research in cultural psychology documents differences in cognitive styles, with East Asian cultures typically showing more holistic thinking patterns, while Western European cultures tend toward more analytic approaches. These differences may reflect coevolution of genes and culture. The individualism prevalent in Western societies versus the collectivism common in East Asian cultures may have roots in both agricultural patterns and disease environments that created different selection pressures on social behavior over thousands of years. Rice agriculture, which dominated East Asia, required coordinated irrigation and labor sharing, potentially selecting for genes that facilitated collective action. Wheat cultivation in Europe demanded less coordination, possibly favoring more independent behavioral tendencies. Similarly, population density and disease patterns differed across Eurasia, potentially creating different selection pressures on genes influencing social behavior and personality. Dense populations with high disease loads might select for different behavioral traits than sparse, isolated groups. These insights challenge both cultural determinism, the idea that culture alone shapes behavior, and genetic determinism, the notion that genes dictate behavior. Instead, they suggest a complex interplay between genes and culture throughout human evolutionary history. The stakes of this understanding are enormous for social harmony in our increasingly diverse societies. Recognizing the complex evolutionary roots of human diversity undermines racist narratives while acknowledging genuine biological variation in a non-hierarchical framework. Simplistic denial of human biological variation leaves a vacuum often filled by pseudoscientific racism. A nuanced, scientifically accurate understanding provides the best defense against both biological determinism and naive claims that human groups are interchangeable. The real story, that human populations followed different adaptive paths to solve similar environmental challenges, offers a middle ground that respects both our shared humanity and our diverse evolutionary histories. But perhaps the highest stakes involve our future. As climate change creates new environmental pressures and genetic technologies offer unprecedented control over our biology, understanding how humans adapted in the past becomes crucial for navigating what lies ahead. Climate models predict that many regions will experience conditions humans haven't faced for thousands of years. Will our diverse adaptations provide the genetic and cultural resources needed to weather these changes, or will we need to rely entirely on technological solutions? The history of human adaptation suggests that our species' greatest strength lies in our diversity, not just cultural diversity, but the biological variation that emerged as different populations solved similar problems through different pathways. This diversity represents humanity's evolutionary insurance policy. The unique adaptations that emerged in different populations provide a reservoir of genetic and cultural solutions that may prove crucial as we face unprecedented environmental challenges. For example, adaptations to high altitude found in Tibetan, Indian, and Ethiopian populations evolved independently through different genetic pathways. Each solution offers unique insights that could inform medical treatments for oxygen-related conditions. Similarly, adaptations to extreme cold found in Arctic populations, heat tolerance in desert dwellers, and disease resistance in various groups all represent different solutions to environmental challenges that may become increasingly relevant in our changing world. Beyond climate, Our distinct evolutionary histories inform how we might approach emerging genetic technologies. As gene editing becomes possible, understanding the complex adaptive landscape of human variation becomes essential for making wise choices. The ability to edit genes doesn't mean we should erase the adaptive diversity shaped by thousands of years of evolution. This diversity likely contains solutions to problems we don't yet understand and adaptations to challenges we haven't yet encountered. The stakes extend to extraterrestrial exploration. If humans eventually establish colonies on Mars or other worlds, the diverse adaptations in our gene pool may provide crucial starting points for adapting to alien environments through both genetic and cultural means. Our investigation has revealed that the distinct physical traits of Europeans and East Asians reflect not a simple response to latitude or climate, but a complex interplay of migration history, cultural innovation, sexual selection, and chance events. This understanding transforms how we view human diversity, not as a hierarchy or a simple product of environmental determinism, but as a testament to our species' remarkable adaptability and the multiple paths we've found to survive in challenging environments. But the most profound implications may be philosophical. The complex history of human adaptation reminds us that we are neither purely biological nor purely cultural beings, but creatures shaped by the continuous dialogue between our genes and our practices. Our biology influences our culture, and our culture shapes our biological evolution. This feedback loop has accelerated human adaptation beyond what genetic change alone could achieve, allowing us to thrive in environments for which we were never originally adapted. And now, as we stand at the threshold of a new era where humans can directly modify our own biology, the stakes of understanding our evolutionary past have never been higher. The choices we make in the coming decades will shape our species' future in unprecedented ways. But to make wise choices about our future, we must first understand the true story of our past. And that story is far more complex and fascinating than most of us have been taught. A story whose final chapters we've only just begun to reveal. As we continue our investigation, we'll uncover the final pieces of this evolutionary puzzle. The crucial evidence that explains why Europeans and East Asians evolved such different physical characteristics despite their recent common ancestry and similar environmental challenges. The answer lies not in a single factor, but in the convergence of multiple forces that were shaping human populations long before modern science could document them, but whose effects persist in our bodies and our cultures to this day. Chapter 8: Competing Theories of Divergence. As we've explored the complex factors shaping human diversity, several competing theories have emerged to explain why Europeans and East Asians evolved such different physical characteristics despite facing similar environmental challenges. Let's examine the strongest contenders. The first and most established theory is environmental determinism. This perspective argues that subtle differences in climate, terrain, and available resources directly shaped human adaptation through natural selection, with each population optimizing for their specific environment. According to this theory, the maritime climate of Europe, with its cloudy skies and humid conditions, selected for different traits than the continental climate of East Asia, characterized by extreme seasonal variations, clear skies, and bitter dry winters. Europeans evolved narrower nasal passages to warm cold, humid air, while East Asians developed facial features that protected against cold, dry winds and snow glare. Skin lightened in both regions to maximize vitamin D, but through different genetic pathways. Environmental determinism explains many observed differences, but struggles with certain anomalies. Why, for instance, did East Asians develop the EDR variant affecting hair, teeth, and sweat glands while Europeans did not, despite both facing cold conditions? The second major theory is sexual selection divergence. This perspective suggests that once initial physical differences emerged through random mutation, they were amplified by culturally specific beauty standards and mate preferences. According to this theory, light eyes and hair became common in European populations not because they conferred survival advantages, but because they were considered attractive and distinctive. Different beauty standards in East Asia selected for different traits. Sexual selection can create rapid evolutionary change even without survival benefits. If certain traits are strongly preferred in mates, They can spread quickly through a population regardless of their effects on survival or reproduction. Evidence for sexual selection includes the distribution of traits like blue eyes, which spread rapidly through European populations despite offering no clear survival advantage. Similarly, certain East Asian features may have been culturally preferred and thus selected for. The timing aligns with this theory. Many distinctive European and East Asian traits emerged after these populations had already adapted to their environments, suggesting that forces beyond simple environmental adaptation were at work. However, sexual selection divergence leaves important questions unanswered. Why would such different beauty standards emerge in the first place? And why would they persist over thousands of years across vast geographic regions? The third major theory is migration pattern complexity. This perspective argues that the complex history of human migrations, bottlenecks, and founder effects shaped the genetic landscape of Eurasia in ways that simple models fail to capture. According to this theory, the physical differences between Europeans and East Asians reflect not just adaptation, but historical contingency. Who happened to migrate where, which random mutations occurred in which populations, and which archaic humans they encountered. Evidence for this theory comes from ancient DNA studies revealing multiple population replacements and admixtures across Eurasia. The genetic landscape was continuously reshuffled, with different adaptive variants rising and falling in frequency through complex demographic processes. The discovery that Europeans received different genetic contributions from Neanderthals than East Asians did from both Neanderthals and Denisovans supports this theory. These archaic admixtures provided ready-made adaptations that shaped subsequent evolution. Migration pattern complexity explains certain anomalies, like why some adaptive traits spread in one population but not another. If the beneficial mutation simply didn't occur in a population, or if demographic events prevented its spread, adaptation would follow different paths. This theory also accounts for the patchy distribution of certain traits. For instance, the EDR variant common in East Asia also appears in Native Americans, but not Europeans, reflecting the complex migration history connecting these populations. However, migration pattern complexity alone doesn't fully explain the persistence of distinct physical characteristics in adjacent populations with significant gene flow. Something must have maintained these differences despite ongoing contact and interbreeding. A fourth theory combines elements of the others: gene-culture coevolution. This perspective proposes that cultural practices created different selection pressures on different populations, driving biological adaptation in distinct directions despite similar environments. According to this theory, cultural innovations like clothing styles, dietary customs, architectural practices, and social structures created unique selection environments that shaped biological evolution. Genes and culture evolved together in feedback loops. Evidence for this theory includes the correlation between dairy farming practices and lactase persistence. Europeans developed a strong cultural tradition of milk consumption, creating selection pressure for the ability to digest milk into adulthood, pressure absent in East Asia. Similarly, different culinary traditions may have created distinct selection pressures on digestive enzymes and taste receptors. Agricultural practices influence population density and disease exposure, potentially selecting for different immune adaptations and social behaviors. Even beauty standards, central to the sexual selection theory, can be seen as cultural adaptations that co-evolved with the genes they were selecting. Cultural preferences and biological traits evolved together, each influencing the other over time. Gene-culture coevolution helps explain why populations in similar environments evolved different traits. It wasn't just the physical environment that shaped adaptation, but the cultural environment each population created through their innovations and practices. This theory also accommodates the evidence for both environmental adaptation and sexual selection, while adding the crucial dimension of cultural practice as a driver of biological change. It represents the most comprehensive explanation currently available. However, even gene-culture coevolution leaves certain questions unanswered. What initiated the divergent cultural practices in the first place? Why did some cultural innovations spread widely while others remained localized? What role did chance play in this process? As we weigh these competing theories, we must consider their relative explanatory power. Environmental determinism explains broad patterns but misses cultural influences. Sexual selection explains certain non-adaptive traits, but not their initial emergence. Migration pattern complexity accounts for historical contingency, but not persistent differences. Gene culture coevolution integrates these perspectives, but raises new questions about the origins of cultural divergence. No single theory fully explains the complex patterns of human adaptation we observe. The truth likely involves elements of all these perspectives, combined with factors we're only beginning to understand through recent scientific advances. In the next chapter, we'll explore these cutting-edge discoveries, findings that shed new light on the puzzle of human diversity and suggest an even more complex and fascinating story behind the different evolutionary paths of Europeans and East Asians. Chapter 9: New Science and Persistent Paradoxes. Recent scientific breakthroughs have transformed our understanding of human adaptation, revealing complexities that earlier theories couldn't address. These discoveries both clarify certain aspects of human diversity and introduce new paradoxes that challenge our assumptions. Perhaps the most significant advancement comes from ancient DNA analysis. By extracting genetic material from archaeological remains, scientists can now directly observe how human genomes changed over time rather than inferring past genetic states from modern populations. These studies have revealed something remarkable. Many characteristic European or East Asian traits are surprisingly recent developments. The distinctive European combination of light skin, hair, and eyes largely emerged after agriculture, less than 10,000 years ago. Similar recent evolution occurred in East Asia. The EDR variant so common in East Asian populations reached its current frequency only within the past 28,000 years. Many features we associate with different populations evolved much more recently than previously thought. This recency contradicts older narratives suggesting these adaptations emerged during the initial migration out of Africa. Instead, they represent ongoing evolution as populations continuously adapted to changing environments and cultural practices. Even more surprisingly, ancient DNA reveals that European populations experienced almost complete genetic turnover several times. Today's Europeans are not direct descendants of Europe's first inhabitants, but result from multiple migration waves that replaced earlier populations. Similar population replacements occurred across Asia. The people who first settled these regions weren't the direct ancestors of modern inhabitants. Instead, waves of migration brought new adaptations, creating a complex layering of genetic influences. This discovery transforms our understanding of human adaptation. Rather than a simple story of populations adapting to local environments, we see a dynamic process of migration, replacement, admixture, and continuous evolution shaped by both environmental and cultural factors. Another breakthrough comes from improved understanding of selection mechanisms. Scientists have identified new forms of natural selection that help explain rapid evolutionary changes in human populations. One such mechanism is soft selective sweeps, where selection acts on multiple beneficial mutations simultaneously rather than on a single advantageous variant. This process can drive faster adaptation than traditional selection models predict. Evidence for soft sweeps appears in genes related to skin pigmentation, where multiple mutations affecting different aspects of melanin production were selected simultaneously in both European and East Asian populations, allowing rapid adaptation to reduced UV exposure. Another mechanism is polygenic adaptation, where selection acts on many genes simultaneously, each with small effects. This process leaves subtler genomic signatures than traditional selective sweeps, but can produce significant phenotypic changes over relatively short time frames. Polygenic adaptation helps explain how complex traits like facial structure, which are influenced by hundreds of genes, could evolve differently in Europeans and East Asians despite ongoing gene flow between these populations. These new selection models resolve certain paradoxes, explaining how human populations could diverge so rapidly. But they introduce new questions. Why would selection pressure be strong enough to drive such rapid changes after humans had already adapted to their environments? The answer may involve another recent discovery: the crucial role of cultural niche construction in human evolution. Humans don't simply adapt to their environments. They transform them through cultural practices, creating new selection pressures in the process. Agriculture represents the most dramatic example. When humans adopted farming, They radically altered their diets, population densities, disease exposures, and social structures. These cultural changes created entirely new selection pressures, driving rapid biological adaptation. In Europe, the transition to agriculture created selection pressure for lactase persistence, alcohol tolerance, and disease resistance against pathogens that thrived in dense farming settlements. These pressures drove significant genetic changes in just a few thousand years. In East Asia, different agricultural practices, particularly rice cultivation, created different selection pressures. The demands of labor-intensive rice farming may have selected for different physical and behavioral adaptations than wheat agriculture in Europe. These insights suggest that the divergence between Europeans and East Asians accelerated after agriculture, not despite cultural similarities, but because of subtle differences in how farming was practiced in each region. Another breakthrough comes from epigenetics, the study of how environmental factors influence gene expression without changing DNA sequences. Epigenetic modifications can be passed down through generations, creating heritable adaptations without genetic mutations. Research suggests that certain population differences may reflect epigenetic adaptations to historical conditions. For example, exposure to famine might trigger epigenetic changes affecting metabolism that persist for several generations. If European and East Asian populations experience different historical stressors, different famines, diseases, climate fluctuations, these could have produced distinct epigenetic adaptations that complement genetic differences between these groups. Perhaps the most surprising recent discovery involves the microbiome, the trillions of bacteria that colonize the human body and influence everything from digestion to immune function. Different populations host distinct microbial communities shaped by diet, environment, and ancestry. Europeans and East Asians have different characteristic microbiomes, reflecting their distinct dietary histories. These microbial differences might explain some physiological variations between populations that cannot be attributed to genetic factors alone. The microbiome represents a form of non-genetic inheritance. Each generation passes its characteristic microbial community to the next. This transmission creates another mechanism through which adaptations can spread within populations without genetic changes. These scientific breakthroughs suggest that human adaptation involves multiple systems operating simultaneously: genetic, epigenetic, microbial, and cultural. The distinct characteristics of Europeans and East Asians reflect differences across all these systems. Yet paradoxes remain. If humans are so adaptable, why do certain physical differences persist even in our globalized world where environmental conditions have largely converged? Why haven't thousands of years of contact erased the distinctions between populations? One explanation involves developmental constraints. Once certain developmental pathways evolve, they can be difficult to modify without disrupting multiple interconnected traits. This developmental inertia may preserve population differences even when selection pressures change. Another factor might be balanced polymorphism, where genetic diversity is actively maintained because different variants are advantageous in different contexts. Human diversity might represent not incomplete adaptation, but adaptive variation maintained by fluctuating selection pressures. Perhaps the most perplexing paradox concerns timing. Why did Europeans and East Asians evolve different physical characteristics in response to similar environments during roughly the same period? Why didn't convergent evolution produce more similar adaptations? The emerging answer involves complex interactions between genetic history, cultural innovation, and chance events. The specific adaptations that emerged in each population reflected not just environmental demands, but the particular genetic and cultural resources available to meet those demands. These scientific breakthroughs and persistent paradoxes bring us closer to understanding the real reason Europeans and East Asians evolved differently. But to fully grasp this complex story, we need to integrate these insights into a comprehensive new model of human adaptation. In the next chapter, we'll reveal this integrated model, the framework that finally explains why Europeans and East Asians developed such different physical characteristics despite their recent common ancestry and similar environmental challenges. Chapter 10: The Adaptive Mosaic Revealed. Throughout this exploration, we've examined competing theories, scientific breakthroughs, and persistent paradoxes surrounding human adaptation. Now we can finally reveal the comprehensive framework that explains why Europeans and East Asians evolved such different physical characteristics. The answer isn't a single factor, but a revolutionary new model called the adaptive mosaic theory. This framework proposes that human adaptation operates as a complex network of interacting systems, genetic, epigenetic, microbial, and cultural, that together create distinct adaptive patterns. Unlike traditional models that treat adaptation as a simple response to environment, the adaptive mosaic theory recognizes that humans adapt through multiple, parallel systems that influence each other through continuous feedback loops. This perspective transforms our understanding of why Europeans and East Asians evolved differently. The distinctive features of each population represent not just adaptations to physical environments, but adaptations to cultural niches, demographic histories, and chance historical contingencies. The theory emerges from cutting-edge research across multiple disciplines. Population genetics reveals how ancestry shapes available genetic variation. Archaeology documents how cultural practices create selection pressures. Epigenetics and microbiome studies reveal non-genetic adaptation mechanisms. Together, these fields paint a picture of human adaptation far more complex than previously recognized, a mosaic of influences rather than a linear response to environment. This complexity explains why superficially similar environments produced such different physical adaptations. Let's apply this framework to understand the divergence between Europeans and East Asians. Both populations faced cold climates and reduced UV exposure after migrating northward from Africa, yet they developed distinct physical characteristics through different adaptive pathways. The adaptive mosaic theory explains this divergence through 5 key mechanisms: ancestral genetic variation, cultural niche construction, sexual selection feedback loops, parallel adaptive pathways, and random founder events. These mechanisms interacted to create distinct adaptive patterns. First, ancestral genetic variation differed between the founding populations of Europe and East Asia. Random mutations present in one founding group, but not the other, provided different raw materials for adaptation, even to similar environmental challenges. Ancient DNA confirms this pattern. The migrants who became Europeans carried different genetic variants than those who populated East Asia. These initial differences, though small, influenced subsequent evolutionary trajectories by making certain adaptations more or less accessible. Second, cultural niche construction created different selection environments despite similar climates. The specific technologies, subsistence patterns, and social structures that evolved in each region generated distinct selection pressures beyond those imposed by the natural environment. For instance, different architectural traditions influenced exposure to smoke, cold, and UV radiation. European stone buildings with central hearths created different respiratory challenges than East Asian paper-walled structures with floor heating systems. Different clothing traditions altered skin exposure to sunlight, potentially explaining why East Asians and Europeans evolved light skin through different genetic pathways. The specific cultural solutions to cold adaptation shaped biological evolution differently in each population. Third, sexual selection operated as a feedback loop with cultural practices. Initial random differences in appearance became amplified through mate preferences, which themselves were shaped by cultural values that differed between regions. These preferences weren't arbitrary, but reflected specific cultural and environmental contexts. Features associated with health, fertility, or social status in one cultural context might carry different signals in another, leading to divergent selection patterns. Fourth, parallel adaptive pathways allowed different genetic solutions to similar problems. When multiple genetic routes can achieve the same adaptive outcome, which pathway a population follows depends on which mutations randomly occur first and which cultural practices develop. Both Europeans and East Asians needed to adapt to reduced UV radiation, but they did so through mutations affecting different genes in the melanin production pathway. The specific pathway followed in each case reflected both random genetic variation and cultural context. Fifth, founder effects and genetic drift played crucial roles, especially during population bottlenecks. Small founding populations carried only a subset of African genetic diversity, and random demographic events could dramatically alter gene frequencies independent of selection. The last glacial maximum around 20,000 years ago forced both European and East Asian populations into restricted refugia, creating bottlenecks that amplified genetic differences. When populations expanded again after the ice retreated, they carried these distinctive genetic signatures. The adaptive mosaic theory reveals that human evolution isn't a simple story of adaptation to environment, but a complex interplay of these five mechanisms operating simultaneously across multiple adaptive systems: genetic, epigenetic, microbial, and cultural. This framework finally explains the paradoxes we've encountered. It explains why populations in similar environments evolved different traits. They followed different adaptive pathways based on their unique genetic and cultural starting points. It explains why adaptation happened so rapidly. Cultural niche construction accelerated evolutionary change by creating strong, novel selection pressures, while multiple adaptive systems allowed changes to accumulate across genetic, epigenetic, and microbial dimensions simultaneously. It explains why certain traits spread in one population but not another. Different cultural practices created different selection pressures, while distinct founding populations carried different initial mutations, making some adaptations more accessible in certain groups. Most importantly, the adaptive mosaic theory fundamentally transforms our understanding of human diversity. The physical differences between Europeans and East Asians aren't simply adaptations to latitude or climate, but complex adaptive responses to unique historical trajectories. These trajectories involved both biological and cultural innovations, both purposeful adaptations and random historical contingencies. The mosaic of human diversity reflects not a hierarchy of advancement, but a beautiful array of solutions to the challenge of survival. This understanding dissolves traditional concepts of race while acknowledging the reality of human biological variation. The visible differences between populations don't reflect discrete categories, but complex adaptive patterns shaped by interacting systems responding to unique historical circumstances. The adaptive mosaic theory has profound implications for medicine, revealing why different populations might respond differently to treatments based on their unique adaptive histories. It explains why certain diseases show population-specific patterns that simple genetic models can't account for. It helps us understand cultural differences not as arbitrary traditions, but as adaptations that co-evolved with biological traits to create integrated adaptive systems. The distinctions between human populations represent different adaptive strategies, each with its own strengths. Perhaps most importantly, this framework offers a new perspective on human identity that transcends both naive biological determinism and extreme cultural constructionism. We are neither simply products of our genes nor blank slates shaped only by culture. Instead, we are adaptive mosaics, complex beings shaped by the continuous dialogue between our biology and our practices, between the genetic legacies we inherit and the cultural niches we construct. The real reason Europeans and Asians evolved differently lies in this mosaic nature of human adaptation, in the unique combinations of genetic heritage, cultural innovation, and historical contingency that shaped each population's evolutionary trajectory. As we conclude our exploration of human evolutionary divergence, we're left not with simple answers, but with a richer understanding of our shared humanity. The story of how Europeans and East Asians evolved different physical characteristics reveals the remarkable adaptability that defines our species. This adaptability operates through multiple, interacting systems: genetic, epigenetic, microbial, and cultural. Together, these systems form the adaptive mosaic that allowed humans to thrive in environments from equatorial forests to Arctic tundra, from arid deserts to mountain plateaus. The diversity we see across human populations doesn't reflect separate evolutionary paths, but different solutions to the challenge of survival. Solutions shaped by both purposeful innovation and chance historical events, by both environmental pressures and cultural choices. Understanding this complexity transforms how we view human differences. The visible variations between populations aren't markers of separate races, but windows into our shared evolutionary history, a history of creative adaptation through both biological and cultural means. This perspective has profound implications for our future. As we face unprecedented challenges from climate change to emerging diseases, our diverse adaptive heritage represents humanity's greatest resource, a reservoir of solutions developed across thousands of years of creative adaptation. The different adaptive strategies preserved in various human populations may contain crucial insights for addressing these challenges. Just as medications developed based on unique population adaptations benefit all humanity, cultural adaptations from diverse societies may offer wisdom we all need. Our journey through human evolutionary history reveals that diversity isn't a problem to be overcome, but a strength to be celebrated. The very feature that has enabled our species to thrive in environments for which we were never originally adapted. This understanding also comes with responsibility. As we gain unprecedented power to alter both our environments and our biology, we must proceed with wisdom informed by our evolutionary past. The complex adaptive systems that shaped human diversity took thousands of years to develop. Yet questions remain. How will human adaptation continue in our increasingly globalized world? Will genetic technologies accelerate or diminish human diversity? How will cultural and biological evolution interact as we face future challenges? These questions have no simple answers, but the framework we've explored, the adaptive mosaic theory, provides a foundation for addressing them with nuance and wisdom. It reminds us that our greatest strength lies not in any single adaptation, but in our adaptive flexibility. As you drift toward sleep tonight, carry with you this richer understanding of your place in the human story. You are part of an adaptive mosaic stretching back to our African origins and forward into possibilities we cannot yet imagine. The real mystery of human evolution isn't simply why Europeans and East Asians developed different traits, but how our species found so many creative paths to survival, paths that converge in the remarkable diversity and fundamental unity of humanity today. If you've enjoyed this exploration of human adaptation, subscribe to our channel for more journeys into the mysteries of our shared past and the possibilities of our collective future. Until next time, sleep well, knowing you're part of the most adaptable species Earth has ever known.